Okay, so in this free response question, in the context of sort of connecting objects in Newton's laws, I'll work on just 4 questions to the entire page, and I'll work on the entire 4 in one video. So the context is there's 2 boxes in the flat frictionless surface table. Box 1 has a mass of 2 kgs, and box 2 has a mass of 3 kgs, and a force of 4.1 newtons acts on box 1 from the left directly 25 degrees below the horizontal. So we can sort of see that geometry if we were to draw a dotted line here. So these 2 angles here and here are the same. So this is also 25 degrees and that's 25 degrees below the horizontal. And the first question is to create 2 free body diagrams for each of the boxes in the space below. So I'll start with the weight forces of box 1 and box 2. So I'll try to draw this somewhat quantitatively correct, but it's going to be difficult to do exactly quantitative given that the weight forces are significantly larger than the actual pushing force. So the weight forces are roughly 20 newtons and 30 newtons. That's about quite 5 to sort of 8 times larger than the pushing force. But I'll label this as the weight force on box 1 by the Earth. So I'm using the notation force. For subcritical letters, the force of the object, the force that's exerted on the object, and then the object exerting that force. And then I'll draw the weight force on box 2 a little bit larger. Should be 1.5 times larger if you want to be exact. So that's the weight force on box 2 by the Earth. For box 2, its normal force essentially is straight upwards, and it balances out this weight force. So these should be the same length. So this is the normal force on box 2 by the table. And those 2 are equal because of Newton's second law, stating that there's no y acceleration of box 2. So these 2 forces have to be equal in magnitude. Now for box 1, it has 2 downward forces, so the downward weight force, and it has a component of this pushing force, so the normal force will not be equal in magnitude to the weight on box 1. So I'll draw in the pushing force. Again, it's not to scale here, but so I'm just going to draw a little bit larger just so it's clear that we can see it. And this will be some sort of pushing force, so it's not perpendicular to the side of box 1, so I can't technically label it a normal force. I'm just going to call it an F. It's difficult to label. It would have probably some normal component and some frictional component. So this is going to be the force on box 1, and I don't know what's exerting that force. I'll just label this as some sort of object X. Maybe it's a hand, but it's not clear what's pushing the boxes. So the normal force on box 1 should be equal in magnitude to the weight force plus this component of this pushing force. So let's label this a little bit larger than the weight. And this is the normal on box 1 by the table. And then box 1 pushes on box 2 to the right. So I'll label this force here. This is the normal on box 2 by box 1. And since box 1 pushes on box 2 to the right, then box 2 has to push on box 1 to the left. And these are the same magnitude. These 2 normal forces in red pen. So this is the normal on box 1 by box 2. And you could show an X here to indicate that these are total law force pairs. And that should be your complete free body diagram. And 3 forces on box 2, the normal by the table, the weight force down, and the pushing force by box 1. There's no friction. And then on box 1 you have, of course, its weight force, the pushing force, the normal force, which is equal to the sum of the weight plus the y component of the pushing force, and then you've got the normal force on box 1 by box 2. That's a total force pair with the normal on 2 by 1. And that should be the full correct diagram for question 13. So in question 14 you were asked what is the acceleration of the two-box system. So to answer this question, we need to we can recognize that the system has a mass of 5 kgs, and if I were to sum up all of these forces, in a sense, sum these two free body diagrams, the two total force pairs, or the forces in the total force pair would cancel. So the only force pushing the whole system to the right is the x component of this pushing force. The sum of the normals would cancel out the sum of the weights, so you'd only be left with the net force on the whole 5 gram system would be the x component of F1x. So the mass of the system is 5 kgs, and the F net on the system is the x component of F1x. So not to confuse these two x's, so this x is just representing some mystery object, and this x is representing the x direction on a coordinate system. So trying to find the acceleration, so the acceleration is F net over m. I'm trying to find we know the F net is going to be 4.1 newtons times the cosine of 25 degrees, so that will give us the x component of this pushing force, divided by the total mass, and I believe this gives 0.74, I think. So 0.74 meters per second squared. Okay, so that should answer question 14. Question 15 is asking what is the magnitude of the force which box 2 exerts on box 1. So you can answer this in two different ways, one shorter than the other, so maybe I'll split it up into two different parts here. So the question asks what is the force at which box 2 exerts on box 1, so you can focus on the forces on box 1, but what the question is asking is the magnitude of the internal forces between the two boxes, which is the total force pair. So the magnitude of on box 1 by box 2 is equal in magnitude to the normal force on box 2 by box 1. But the normal force on box 2 by box 1 happens to be the net force on box 2, because there's no friction in the system. So this is equal to F net 2. So the short version, I'm going to put in magnitude here. So the short version is to, even though the question asks about a force on box 1, recognizing that it's a total force pair, you can shorten the solution to just this value to do F net 2 equals N21, and I'll use this just to indicate magnitude, is M2 times A. So N21 would be equal to the mass of box 2, the 3 kgs, times the 0.74 meters per second squared from the previous question, and that gives you 2.2 newtons. That's the correct answer. So that's a way to do it from the box 2 analysis. So if F21 is 2.2 newtons, that's also the magnitude of F12, which is what the question is asking. You could also focus on box 1, which in a sense in this particular case, so if you think about the forces that are on box 1 in the x direction, so F net 1 would be equal to the F1x in the x direction minus the N12, and that would be equal to M1 times A, and A of the whole system, A of 1 equals A of 2 equals A of the system. So you can solve N12 will be equal to F1 x in the x direction minus m1a. So it takes a little extra step, but not much. So you can say 4.1 newtons times the cosine of 25 minus 2 kgs, the mass of box 1 times the acceleration of the system. And this should also give you 2.2 newtons. So it's just a little bit longer, but should give you, has to give you the exact same answer. And then for the last question, we're introducing a friction force. So the box encounter rough patch produces a total friction force of 1.2 newtons. What's the new acceleration of the system? So in this case, the net force on the system is not just the x component of the pushing force, but you'd have to take into account the friction. So F net of the system in this case is going to be F1x in the x direction minus the friction force on the system by the floor or the table, and that has to equal the mass of the system times the A of the system. So we're trying to find the new acceleration. So the A of the system would equal that F1x in the x direction minus the friction on the system, all divided by the mass of the system. So we take that original F1 pushing force in its x component, 4.1 newtons, times the cosine of 25 degrees, minus the 1.2 newtons. The frictional force will always oppose the motion, so it will be in the opposite direction to the pushing force. And then divide all that by the 5 kgs, the mass of the system. And that gives you a new acceleration, which of course has to be smaller than the non-frictional case of 0.74, so the new answer is 0.5 meters per second squared. So should expect it to be smaller than the acceleration that we saw in question 14. And that should be the 3 questions from 13 to 16.